What are oxidation and reduction? Well, oxidation is the loss of electrons, while the reduction is the gain of electrons. We can remember this through an acronym called OIL-REG. The species that get oxidized is called the reducing agent, and the species that get reduced is called the oxidizing agent. We can also state the oxidation number of compounds and elements using these rules. The oxidation number of oxygen is always -2, except in peroxide and oxygen difluoride. And the oxidation state of hydrogen is always +1, except in metal hydrides. In the first example, we have carbon dioxide, and we want to find the oxidation number of carbon. Knowing that in this case the oxidation number of oxygen is -2, we can use quick algebra to figure out the oxidation number of carbon, which comes to be +4. For the second example, we have sulfate ion, and we want to figure out the oxidation number of sulfur. Again, using quick algebra, we are able to figure out the number of sulfur is +6. This is because the charge of sulfur and 4 oxygen must add up to -2. Finally, this example of peroxide. Sodium is a group 1 metal, so the oxidation number has to be +1. Oxygen, therefore, must be -1, which makes sense since oxygen always has a -1 charge in peroxides. Balancing half reactions. A common way to balance a half reaction is through a process called OHE. The first O represents other, which means to balance all other atoms besides oxygen and hydrogen. The second O represents oxygen, which means to balance oxygen by adding water molecules. The H represents hydrogen, which means to balance hydrogen by adding hydrogen ions. And finally, the E represents electrons, which means to balance the total charge of reactants and products by adding electrons to the most positive or the least negative side. In this reaction, we can see we need to balance two half reactions. The tin is getting oxidized since it is losing electrons, where the permanganate ion are getting reduced because they are gaining electrons. Let's first take a look at the oxidation part. Going through the process OHE, we notice no other atoms need to be balanced, and oxygen nor hydrogen need to be balanced. This leaves us to balance the total charge. The reactants have a charge of +2, while the products have a charge of +4, so we need to add 2 electrons to the most positive side, in this case the product side. Now let's take a look at the reduction reaction. Other atoms in this reaction are also balanced, so we move down to oxygen. Here the reactants have 4 oxygen while the products only have 2. Therefore we must add 2 molecules of water to balance the oxygen. Now we can move down to the hydrogen. By adding 2 water molecules, we have added 4 hydrogen molecules to the product side. So we must balance that by adding 4 hydrogen ions to the reactant side. Finally, the charge. The products have a charge of 0 and the reactants have a charge of +3. So we must add 3 electrons to the reactant side, since it is the most positive side. Now to create the final equation, we must cancel the electrons of both reactions. As you can see, the first reaction has 2 electrons, while the second reaction has 3 electrons. So we can multiply the first by a factor of 3 and the second equation by a factor of 2, which will cancel out the electrons, giving us the final reaction. Reading the question, it will tell you if the reaction occurs in acidic or basic solution. If it has occurred in an acidic solution, you can leave the reaction as it is. But if it was in a basic environment, we have to add hydroxide ions to both sides. Standard reduction potential table and spontaneity. The standard reduction potential table plays a major role in electrochemistry. For starters, the strongest oxidizing agent will be found on the top left of the table, and the strength increases as you move up the table. On the other hand, the strongest reducing agent will be found on the bottom right of the table, and the strength of the reducing agent increases from top to bottom. The unit of these reactions is called voltage. The voltage value of a reaction is based relative to the reaction of hydrogen, which has a voltage of 0. Here are some quick tips about the SRP table. To start off with, the predominant redox reaction will occur between the strongest oxidizing agent and the strongest reducing agent. When the oxidizing agent is above the reducing agent, we call this reaction to be spontaneous because the E0 net will be positive. Another tip would be when we flip a reaction, we must change the sign of the voltage. But when we multiply the reaction to balance electrons by a factor x, no change in the voltage will occur. Here's an example about this topic. Label all oxidizing agent and reducing agent. State whether or not this reaction is spontaneous. By looking at the net reaction, we are able to find out the diatomic iodine is the oxidizing agent and the fluorine ions are the reducing agent. Since the iodine gets reduced, it has a E0 value of 0.54 volts. The fluorine ions are getting oxidized, so they have an E0 value of negative 2.87 volts. We flip the reaction, therefore we have a negative E0 value. Since we get a negative number for our E0 net, this reaction must be non-spontaneous.
When we do a redox titration, we still apply all the basic principles of titrations. Our apparatus would mainly consist of a burette attached to a ring stand with a burette clamp, an Erlenmeyer flask, a magnetic mixer, and a pipette with a suction bulb. In a redox titration, we titrate an oxidizing agent with a reducing agent, or vice versa. Just like how the indicator of an acid-base titration is itself a weak acid with a different color in its base form, the indicator of a redox titration can be a reducing agent with a different color in its oxidized form. In redox titrations, the titrant often acts as its own indicator. Let's say we use the permanganate ion as a titrant. Under acidic conditions, the permanganate ion is reduced to the manganese 2+ ion, which is a faint pink color. When we add this permanganate solution to the reducing agent of unknown molarity, the permanganate ion is reduced and the purple color disappears. At some point, the chemical species that was reducing the permanganate has been totally consumed, and after adding 1 drop of the permanganate, the purple color will remain. This signals that the equivalence point has been reached. Here we are asked to find what the concentration of iron 2 ions was after titrating a 25 milliliter solution of iron 2 ions to the equivalence point, while using 18.02 milliliters of 0.0149 molar permanganate ion in acidic solution. We always begin by writing the balanced net ionic equation for the titration reaction, which we get from combining the half reactions of the iron 2 ion and the permanganate ion. We take our volume of permanganate used and use it to find the moles of iron 2 ions that were in the 25 milliliter sample. We can then divide the moles of iron 2 ions by the initial volume to give us the concentration in the original sample. An electrochemical cell provides power by converting chemical energy into electrical energy. The electricity comes from a spontaneous redox reaction within the cell. Electrochemical cells consist of an oxidation half reaction that is isolated from a reduction half reaction. The predominant redox reaction will be between the strongest available oxidizing agent and the strongest available reducing agent. The simplest half cell consists of a metal electrode immersed in a solution containing ions of the same metal. One of the metal electrodes gives electrons to the other half cell. In this cell, there is one half cell with a magnesium electrode immersed in a solution containing magnesium ions. The other half cell has a copper electrode immersed in a solution containing copper 2 ions. We use our standard reduction potential table to predict which electrode is the anode and which is the cathode. Oxidation occurs at the anode while reduction occurs at the cathode. Magnesium is the strongest reducing agent, so it will be oxidized. Therefore, the magnesium electrode must be the anode. Copper 2 ions will be reduced at the cathode, which is the copper electrode. Electrons will flow through the wire from the anode to the cathode, and the voltmeter will measure the potential difference. While the magnesium anode loses mass as magnesium metal is converted into magnesium ions, the copper cathode increases in mass as copper 2 ions are reduced to form copper metal. Anions migrate towards the anode, while cations migrate towards the cathode. The salt bridge allows ion migration, and without it, a charge buildup would occur. Another kind of half cell contains a nonmetal electrode immersed in a solution containing ions of the same nonmetal. These look like an inverted test tube, filled with a liquid or gas with a platinum wire running through this liquid or gas. This connects to a piece of platinum foil, where most of the electron transfer occurs. The gas is inserted into the tube through the sidearm. Voltage, or potential difference, is the difference in electrical potential energy between 2 points in a circuit. To determine the voltage of a standard cell, we write each half reaction and its standard potential. We react the strongest reducing agent with the strongest oxidizing agent. In an electrochemical cell, the reduction reaction is always above the oxidation reaction on the SRP table. If we need to flip one of the equations, we must change the sign of its potential. We then add the two equations, making sure the electron gain in one and the electron loss in the other is equal. This might require multiplying one or both equations by a value. This doesn't change the potential of the half reactions, as voltage is joules per coulomb. We then find the sum of the half reaction potentials to give us our voltage of the standard cell. All E0 values in the table are reported relative to the hydrogen gas half cell. In electrochemical cells, E0 should be positive. A cell's condition usually changes as it operates and its voltage drops. As the cell operates, the electrons travel from the anode to the cathode. The concentration of the ion that is reduced at the cathode decreases, while the concentration of the ion being produced at the anode increases. The increasing ion increases its pulling force, while the decreasing ion decreases its pulling force. Eventually, these two pulling forces become equal, and the cell now has 0 volts, so it is dead. The redox reaction has stopped. A great way to describe the change in voltage over time is using the Nernst equation. N is the number of electrons transferred, and Q is the ratio of the ions on the right side of the redox reaction to the ions on the left side. In this example, we want to find the voltage for a standard zinc ion, tin 2 ion cell, after we have changed the concentration of the tin 2 ion. Once again, we start by finding the net redox reaction and the E0 value. If the ion on the left side of the redox reaction is increased, then Q will become less than 1, and log Q will become negative. This means you are now adding a number, resulting in a greater voltage. We know that an electrochemical cell converts chemical energy into electrical energy. However, an electrolytic cell converts electrical energy into chemical energy. This means that instead of generating electrical energy, electrolytic cells use electricity. Other differences between electrolytic cells and electrochemical cells include the fact that electrolytic cells require a DC voltage source, are endothermic, are one cell, don't have a salt bridge, contain a non-spontaneous redox reaction, and E0 is negative. The oxidation half reaction is above the reduction half reaction in the SRP table, and the half reactions that are closest together in the SRP table will occur. This requires the least possible voltage to drive the cell. This is an example of an electrolytic cell with platinum electrodes in nickel 2 bromide solution. Oxidation occurs at the anode while reduction occurs at the cathode, just like in an electrochemical cell. Here, bromide plays the role of the reducing agent, so it gets oxidized at the anode. At the other electrode, which must be the cathode, the nickel 2 ion is reduced. There must be a continuous path from the source's anode to the cathode for an electric current to exist. This is called a circuit. An oxidizing agent, in this case the nickel 2 ions, picks up the electrons from the cathode, while a reducing agent, the bromide ions, donates electrons at the anode. An electrolytic cell needs a voltage source to operate, which might be some kind of electrochemical cell. The electrochemical cell's anode connects to the electrolytic cell's cathode. Unlike electrochemical cells, electrolytic cells do not require a salt bridge to operate. 3 different kinds of electrolytic cells exist. In type 1 cells, there are inert electrodes, typically graphite or platinum, immersed in a molten ionic compound. The molten ions are the only things that can be oxidized or reduced. In type 2 cells, there are inert electrodes, typically graphite or platinum, immersed in an aqueous ionic solution. The ions and water are the only things that can be oxidized or reduced. In type 3 cells, there are non-inert electrodes immersed in an aqueous ionic solution. The ions, water, and the anode can be oxidized, and the ions and water can be reduced. Overpotential is the potential difference between a half reaction's reduction potential on the SRP table and the potential at which the redox event is experimentally observed. Water's oxidation and reduction half reactions have particularly high overpotentials. These half reactions must be moved relative to the others in the SRP table when they are under electrolytic conditions. Due to the overpotential effect in electrolytic cells, Water is a weaker reducing agent than bromide and chloride, and a weaker oxidizing agent than zinc ions, chromium-3 ions, and iron-2 ions. Let's try calculating the voltage required to run a nickel bromide cell. To identify the half reactions occurring, we must once again turn to the SRP table. We identify all the reducing agents and oxidizing agents in our cell, which includes water. Bromide is the strongest reducing agent due to the overpotential of water. The nickel ions are the strongest oxidizing agent. We then add the correct half reactions and their potentials together to give us the overall reaction. From this we can determine the voltage required for the electrolytic cell.
Electrochemical applications, batteries and corrosion. Remember, electrochemical cells are the ones that produce energy due to them having a positive E0 net value. Batteries are common electrochemical applications, and there are three types of batteries. We will first be looking at an alkaline cell, which are commonly found in our TV remotes, toy cars, etc. The anode of these batteries is zinc powder, and the cathode is a compound called manganese 4 oxide plus carbon powder. Finally, the electrolyte is potassium hydroxide paste. We can see the zinc gets oxidized at the anode and the manganese 4 oxide gets reduced on the cathode, producing a positive voltage. The lead acid storage battery is commonly found in your cars. The anode of these batteries is lead, and the cathode is a compound called lead 4 oxide. This battery is called a wet battery due to its electrolyte being sulfuric acid. Finally, the last electrochemical cell is called the fuel cell. Fuel cells are found mostly in electric cars or rocket ships. The anode is the site of oxidation of hydrogen gas, and the cathode is the site of reduction of oxygen gas. The electrodes in this case are inert carbon. Not only does this reaction provide electricity, but also water as a byproduct. Corrosion is a chemical reaction which involves the surface of a metal changing from an element to a compound. For iron, it is when iron metal turns into a compound called iron 3 oxide. Corrosion usually occurs in the presence of water or oxygen gas. Corrosion occurs slowly, and it can also weaken the metal. A common example of corrosion is rust. There are two ways we can prevent corrosion to occur. The first way is cathodic protection. In this process, a sacrificial metal is attached to a metal that is a stronger reducing agent than the metal that you do not want to corrode. The oxidizing agent draws electrons from the sacrificial metal through the metal that is being protected. The second process is called galvanizing. In this, the metal you are trying to protect, commonly iron, is coated with a thin layer of zinc. When zinc gets oxidized, a compound is formed called zinc oxide. Zinc oxide forms a shell around the metal that is being protected. The hard shell prevents any water from reacting with the metal that is underneath. Electrolytic applications. There are three types of applications when it comes to electrolytic cells. The first one is called electrowinning. Electrowinning is a metallurgic term for the electrolytic process of recovering metal from the solution of its ions. This is mainly used in the mining industry. In this process, ions are reduced at the cathode where they are deposited as a metal, which can be later on collected. The second common application is electroplating. Electroplating is an electrolytic process where a metal is coated with a thin layer of a different metal. For example, silver in this case is being coated with copper in a solution of copper sulfate. In this case, copper is the strongest reducing agent and copper ions are the strongest oxidizing agent. Therefore, this reaction can occur and silver will be coated with copper.
Electrorefining is an electrolytic process that is usually performed in the mining industry. Through electrorefining, we can take impurities out of a metal by having a pure cathode attached to an impure anode. In this diagram, an impure anode contains copper, zinc, and gold, while the pure cathode is made up of only copper. Copper and zinc, which have greater oxidation potentials than gold, are oxidized. Gold will not be oxidized and will collect on the bottom of the container as anode sludge. Since copper 2 ions have a greater reduction potential than zinc ions, they will be reduced at the cathode. The other applications for electrolytic cells are called the Eruhol process and the chloralkali process. The Hall process is a major industrial process for smelting aluminum. It requires dissolving aluminum oxide in molten cryolite. The chlor-alkali process is where sodium hydroxide and chlorine are produced by using a solution of sodium chloride. Faraday's law states that the amount of substance produced or consumed at each electrode is directly proportional to the coulombs of charge flowing through an electrolytic cell. This allows us to calculate the mass of a product formed or reactant consumed by using the electrical current. In these calculations, we use the Faraday constant, which is 96,500 coulombs per mole of electrons. If we want to find the current needed to deposit 10 grams of gold in 1.75 hours from a solution containing gold-3 ions, then we begin by writing the balanced chemical equation. We convert 5 grams of gold to moles of gold, moles of electrons, and then use the Faraday constant to convert to coulombs. Current is coulombs per second, so we divide by the time to get our answer. The free energy of a redox reaction provides electrical energy to do the work to move electrons across an electrical potential difference. This equation allows us to find the free energy of a reaction by using the moles of electrons, Faraday's constant, and the potential difference. Because these processes are not 100% efficient, the experimentally determined values will be less than the values we calculate. We include a negative sign because spontaneous processes have a positive E0 value and negative delta G values. We can actually relate free energy, cell potential, and the equilibrium constant using the equations we've learned throughout this course. From this we can see that thermodynamically favorable processes always have positive E0 values and therefore have free energy values that are negative. When delta G is negative or E0 is positive, then K must be greater than 1. Here we want to calculate E0 and delta G when chromium metal is dissolved in nitric acid. First, we combine the half reactions to get E0 for the cell. We then substitute our known values into the equation to give us a delta G value that ends up being negative 984 kilojoules per mole of reaction. The process must be thermodynamically favorable since we get a negative free energy value.